me get to the page. Okay, let me start broadcasting the HDMI so you all can scan the code. Okay. Okay. While the QR code is popping up here on the screen, let's turn it on the laptop. And boom, there we go. All right. So I haven't posted the grades yet to submittal 1. I mean, all in all, everybody did well, but there are a couple of issues that I wanted to go through with everybody, and I'm afraid that if I send you your grade reports, you might miss this. So I wanted to go through a couple things, okay, just to sort of make a point. Just so everybody's aware, what I'm going to do is I'm going to email you all a grade report for the submittal 1, and it's going to be very much like the exam grade reports, right? But there's something that's really kind of important, or a couple things that are important. Okay, so first off, let's take this truss, okay? Does anybody see a problem with this truss? And mainly, the problem is right there. Why are you shaking your head yes? The problem stated that you needed a joint at midspan at the bottom. I don't see a joint at midspan at the bottom. There's one up here, but that's not where we're evaluating deflections. We're evaluating deflections at the bottom. And so there were a lot of you that did the project and said, I want to pick this truss. And this doesn't work, okay? So what's going to happen, and I'm going to go through the other issues, but what's going to happen is I'm going to go and send the grade reports out, but then I'm also going to send out a separate email. And so if you selected a truss that violated one of these conditions, what I'm going to say is, just a heads up, you're going to have to redo, or you're going to have to pick another choice, or you're going to have to redo your design a little bit, okay? And I'm sending you that sort of as a friendly reminder, because I'm using a rubric to grade the submittal 1, and some of you did a fantastic job on submittal 1, but that one little error is enough to say, no, you can't actually use that truss, okay? And so I'm doing that as a courtesy so that you don't go, oh, I got a 27 out of 30, that means I did a good job, I could just use that truss. No, it's going to make, like, the project isn't going to work, okay? So I'm just telling you all that in advance. Does that make sense? So if you get one of those, emails, like either, pay attention to it. If you got any questions, come see me. Otherwise, just, don't worry about it. A couple of other things worth mentioning. I want to take a look at this truss right here, okay? So I have here a truss where this is 20 feet. Okay, everybody watch this. This is 20 feet. This is 16 feet, okay? How long is this member? 4. That member is greater than 22 feet. It can't be longer than 22 feet, right? The member lengths are limited to 22 feet, okay? So, and you might have picked a truss like this. Guess what? It doesn't work, right? So you're going to have to adjust your design a little bit, okay? So I'm telling you this now, okay? Just so that everybody kind of is aware of this, okay? Does that make sense? Okay? Now this is issue number 3. This is not... this doesn't inhibit whether or not your truss is wrong, or the incorrect choice, but I did want to mention it. I had a lot of, like, here's truss 1, here's truss 2, here's truss 3, and this is literally all it said, okay? And there were not enough dimensions to say, well, how long's that? How high is that? It just said, oh, it's 120 feet long. And so the third issue was that there were a lot of schematics that were ill-dimensioned, I guess you could say. Like, there just wasn't enough data. Or, I mean, I had a lot of schematics that here's the truss, and all it said was, this is 16 feet. That's it. So how am I supposed to know whether, how long this is, how long the diagonal is? Like, there was no data on that at all, okay? So that made it a little longer to grade than normal. So, and I mentioned that not really so much for submittal 1, but for submittal 2. You have to submit a CAD drawing, okay, of the final truss layout and all that. And so if you're doing that, and I don't even know what the dimensions are, that's a poor CAD drawing, okay? So everybody okay with that? Okay, so I'm just saying that now so that you're aware when you do your second submission, you kind of know what's going on. Okay, any questions? All right. So you'll get your grade reports either later today or maybe sometime tomorrow, but on Monday I'm going to submit or I'm going to assign submittal 2, okay? And it won't be due till the Friday before Thanksgiving break, so, and you wouldn't even really be able to start that until after today's lecture anyway. So, sound good? Okay, all right, so I'm going to assign homework 7 today. It is not due until Wednesday, okay? So you don't have a homework due over the weekend, okay? But it's not to say you can't start on it, and you'll see what I mean. Let's get into Mastan, okay? Now, you all can go ahead and open Mastan on your computers, but I would kind of like you to, because everybody brought their laptops, right? Everybody brought their laptops. Everybody brought their laptops. Okay, so, okay, I want to talk a little bit about why we use software to do structural analysis, and maybe more specifically, how we go about it, okay? And I want to have a real honest discussion about indeterminate structures, because we haven't talked about that yet. But let's take a step back and talk about just what Mastan is first. So first off, Mastan, it is a software package that will do structural analysis on pretty much any one-dimensional structure like this that we've been talking about this semester. I like Mastan for a number of reasons. It's really easy to learn, and it's very powerful for what it can do. It's pretty powerful. It packs a lot of punch. It's 100% free. It's Apple's friendly, or it's Windows friendly and Apple friendly. I shout out to Ron Zemian, who's a professor at Bucknell University, who makes it available for free. It's an awesome service he's giving to the industry. Like I said, it's really powerful. It can do linear analysis, nonlinear analysis. It can do buckling analysis. It can do second order. I mean, you can do a lot of really, really cool stuff. We're just going to do simple stuff in here, linear elastic analysis in 2D. Just know that Mastan can handle a lot more, okay? It can handle determinate structures and indeterminate structures with ease. The method that it uses, it doesn't matter what the structural analysis method, what the model is. If it's determinate, indeterminate, the method doesn't care. You could use it later for capstone or steel or concrete or whatever. You could use it for later on in your career. There are some limitations. It cannot handle triangular loads. It cannot handle trapezoidal loads. It's the one thing it can't handle. And also it can't handle moving loads. We haven't really talked about moving loads. We're going to talk about that later. If you are feeling adventurous, the source code's available, and you could program triangular loads in there. But we'd have to have some discussion about how to do that. I don't know that we're going to get to that this semester. Let's talk a little bit about indeterminate structures. And so this entire semester, okay, let's go back to the very first topic that we did in here. Remember I sub E, the formula that you use to determine whether or not a structure is unstable, statically determinate, or statically indeterminate? Y'all remember that? So let's talk about indeterminate structures. Okay? An indeterminate structure is one where there's more unknowns than there are equations of equilibrium, which makes the problem harder to analyze from a mathematical standpoint. So one question that engineers often ask is, why use them? If it's harder to analyze, why would you make your life harder? What is the point of using a structure that is more difficult to analyze? Okay? One reason is the response. You get less forces and less deformations in an indeterminate structure, so you can use smaller elements. And if you're using smaller elements in that structure, you're saving money, right? So, for example, let's take a look at a simply supported beam subjected to a uniformly distributed load. I propose that the maximum bending moment is WL squared over 8. And if you calculate this or derive this, you can find that the maximum displacement, the maximum deflection, is 5WL to the 4th over 384 EI. This is a determinate structure because it's simply supported. Now, if I were to take the two ends that are simple supports and replace them with fixed supports, this would become an indeterminate structure. Okay? You cannot solve this with just equations of equilibrium. Okay? But look at the resulting displacement. It is deflecting 20% of the original structure, right? We reduced the deflection by 80%. And then the resulting bending moments go from WL squared over 8 to WL squared over 12 and WL squared over 24. So we can use a smaller beam by fixing the ends, and that saves some money. Okay? Here's another reason. Okay? If you have a beam, right, that's determinate, let's say you have a bridge and there's a pier in the middle and you put a hinge there, If you put a hinge there, that makes it statically determinate, which means you can analyze it. But if that pier fails, that bridge is going in the river, okay? That doesn't happen if the structure is indeterminate, because you can remove the beam and the structure is statically stable. That doesn't mean that the structure has the same amount of strength necessary to support the traffic loads, but in a scenario like that, you're more just interested in making sure that people can get off the bridge all right. And making sure that the structure is at least statically stable could help in that regards, okay? So there are reasons to make a structure indeterminate, okay? So I guess a question would be, and this is where I want everybody to sort of follow along with me on the slides, is how would you deal with an indeterminate structure? Like, how would you analyze this structure, okay? So first off, let's take a look at the structure. How many reactions do we have? How many support reactions total are on this structure? 4. Right? Because there's one for each roller and 2 here, right? And there's no internal hinges, so I is 1, right? So there's 1 too many unknowns, okay? So what that means, here's what that means. I have 4 unknowns. Or, I'm using zeros, that's wrong. I need to use question marks. Those are my 4 unknowns for the problem, right? These are the 4 unknowns. And I propose that in order to do this problem, I need 4 known equations, right? And right now I only have 3. I have that, and that. I can't solve this problem without another equation, right? I can't do it, okay? All right? So again, there's 4 reactions, but we only have 3 equations of equilibrium. So what I need is I need another equation. I need another equation to go in here, okay? And I propose that the equation that I could use is that, okay? In other words, I propose that the vertical deflection at B is 0. Okay, is everybody with me on that? So, okay, that's great, but how do I use that? How do I use it? What do I do? Okay, so here's what I propose that we do. Okay, I propose that we take this structure and remove the roller at B. Get rid of it. Okay, so what that would create is a simply supported beam, right? It would create a simply supported beam. You know, here's the beam. Here's the beam. There's distributed load here. There's a load there. And if I remove the roller, I propose that the structure will be allowed to deform, right? So I guess my question is, what would the displacement be at B, right? Now, is that a problem you all can do in this class? You all can do that, right? Okay, so we should remove the roller and let it deform. Now, for this problem with all these loads and all this data, if you do the math, you'll get the displacement is something like 4.22 inches, okay? But that's not the real displacement. The real displacement is 0, right? Okay? So what I would then say is, okay, now let's look at this structure. Now let's take the structure like this, and now let's push up on it. Let's push up on it right here, and let's figure out what this load needs to be so that that displacement is 4.22 inches upwards, right? So that these loads plus these loads result in a structure that has 0 deformation, right? And so I superimposed all that together. So basically I'm figuring out what's the necessary force to push the beam back up 4.22 inches. So I do that structural analysis problem, and I get a number of 63.75 kips, right? So what I would basically say is, okay, here's my 4 equations and 4 unknowns, and the idea is, okay, I'll use this one to figure out that this is 63.75 kips upward, and now I've got 3 equations, 3 unknowns, and I could treat it like any other problem I've done this whole semester, right? Okay? The name for this is the method of consistent deformations, okay? It is what I would call the easiest method to understand, okay? Just brute force the thing, okay? Everybody with me kind of on the method? Okay, all right. And so we just use statics, get an AX of 0, AY of this, CY of this, and shear diagram, moment diagram, all that hullabaloo. Okay, now, that is the method of consistent deformations. And if I was doing a problem like this by hand, and this was all I had to worry about, I would use this. The problem is, this is a very bad method for programs, for software. So let me give you an example of what I mean. We chose this support as what I'll call our redundant, this support here at B. Could we have chosen the support at C? What about the support at A? Would it have changed how we did the problem? Yes. It wouldn't change the answer, but the approach that we used would have been very, very different, okay? And the problem with that is it makes it difficult to standardize and difficult to write a program for, okay? And we're only talking about a problem that only has one redundant, or an I value of 1. What if we had a problem that had an I value of 74? Okay, and you might think that's a crazy number, but that's not crazy if we're talking about real-world structures, right? So being able to write a program as the number of redundants increases is very, very difficult, okay? And so as a result, I mean, and in order to deal with problems like this, engineers for decades and decades have developed oodles and oodles of methods for analyzing indeterminate structures. And if you open up your textbook, start at, you know, I mean, the second half of the textbook is all different methods to analyze indeterminate structures. And there's oodles of chapters, but they can basically be broken up into two categories. What I'll call a flexibility method. A flexibility method would be something like this, where the goal is to figure out unknown forces, right, like unknown reactions. But then the second, that's a flexibility method, but the inverse of that is what's called a stiffness method. And a stiffness method is, the idea is to solve for unknown deflections. And the advantage of a stiffness method is it's very, very easy to standardize, okay? And I'm going to explain how that works, and I'm going to give you an insight into matrix analysis. Matrix analysis is going to be the last thing we talk about this semester, and matrix analysis is going to explain how MASTAN works. And it doesn't matter if it's MASTAN or Abacus or ANSYS or COMSOL, they all work the same way. And so we're going to explain sort of the background as to how this stuff works. Let me give you an example. Okay, let's talk about a very, very, very basic problem. This should remind you of Engineering 216 last semester. So I got a bar and I yank on it, okay? I yank on it and it displaces some degree delta, right? And so you know that I can compute delta as FL over EA, right? I take the force times the length divided by EA, right? Okay, so if I rearrange this a little bit, I can say this. I can say I'm going to flip and multiply, and I'm going to say that F equals delta times this. I'm just rearranging it. And that fraction, EA over L, I'm going to give that a name. I'm going to call it K, okay? And I'm going to propose this term K is what's called a stiffness. See, basically what I'm doing is I'm trying to treat this problem like a spring problem from physics. Remember spring problems from physics where you had a spring constant and it displaced in F equals Kx? Remember that? It's kind of the same idea. All right? So I propose, this is what I propose. For a single bar, we have fully analytically solved the problem. We figured it out, F equals K delta, okay? This is the solution for a single bar, okay? And my proposal is, what's different between that and this? This is just a bunch of bars, okay? And the term I'm using, and you're going to understand why I'm using this term later, the term I'm using is an assemblage of bars, okay? And so the idea is, what I can do is represent this with matrix algebra. Instead of force equals stiffness times, stiffness times displacement equals force, I can say a stiffness matrix times a displacement vector equals a force vector, okay? And I can solve for the system that way. Why is that? Why does that matter? Because computers can do linear algebra and matrix algebra like that. Right? A computer is really built to do two things, count and add, right? When you're playing Fortnite, that's all it's doing. It's just doing a lot of them, right? But that's basically it. It's just counting and adding. Computers can do that all day, any day. Okay? Computers love that. And so what we can do is we can use a computer's nascent ability to solve these types of equations to do a lot of really fancy stuff. And we can we can do some pretty powerful stuff. And the other advantage of matrix analysis is that we can standardize this approach. And so I'll show you how matrix analysis works. Now today, what we're going to worry about is this blue box and then the blue box at the very end, okay? So the way matrix analysis works is the first thing that you do is you create the model. In the business, we use the term pre-processing. And so pre-processing is things like creating the geometry, so like the members, the joints, the boundary conditions, creating the loads, and creating the stiffness. So the material properties, the section properties, so on and so forth. And then what's going to happen is there's this little button on the software package called Solve or Analyze. And you click the button, it just gives you all the answers. It's really crazy, right? But let me show you a little bit of the background as to what MASTAN or any of these programs are doing. So it sort of works generally in a four-step process. So the first thing that it's going to do is it's going to write the stiffness matrix or the spring matrix. Remember, this is sort of our goal here. Our goal here is to try and formulate it like this, like force equals K times delta. That's sort of our goal. So the first thing that it does is it writes the spring matrix or the K matrix for the whole system. And so the way that it does that is it takes a spring matrix for each member and it assembles it into a big old K matrix for the whole system. Then what it does is it writes the force vector. Usually the force vector, you can honestly just write it. You can just look at it and write it. If you have member forces like with beams, it's a little tricky, but by and large you can just look at it and write it. And so if you have the F vector and you have the K matrix, you can just invert the K matrix and solve for the displacements. What you have to do is you have to knock out the rows and columns associated with the boundary conditions and then just let Excel or MATLAB, I know MATLAB's like, but by and large you can just let a software program do it. It'll solve for the displacements. Then what you do is you break those displacements up and you back substitute them in and get the forces in each member, get the reactions. And that's it. Okay, that's basically matrix analysis in a nutshell. Now we're not going to see that happen today. All we're going to see is we're going to do this, press a button, MASTAN's going to do all this and give us the answer. And so dealing with the final answer is what's called post-processing. Post-processing is going to be things like looking at the support reactions, looking at the member forces, the internal member forces, looking at the deflected shape, etc. These are some applications of FEA. So for example, you can use it in geotech land, you can use it in thermal land. These are some models that I built when I was doing my research for my dissertation. These are some bridge models of some press brake form tub girders. And so you can do some pretty cool stuff with it. Matrix analysis for finite elements works really well with different geometries. Okay, let's actually start getting into doing some matrix analysis. Now, you all, I can't stop you from just going ahead and starting with this tutorial, but I would advise you to just give me a couple minutes to explain some things with matrix analysis, so that as I start going down this road, I'm going to give you 3, and then you can pass this down. Thank you. As we start going down the rabbit hole of matrix analysis, I'll be able to make your lives a little easier. Okay. All right, so first off, if you haven't opened MASTAN yet, go ahead and open it. MASTAN looks pretty boring when you first open it. You can pass those down. MASTAN works in a very, very straightforward fashion though. So if you look up top, okay, up top there are these menus, okay, and literally what we're going to do is start here and just work our way across. Like do everything we need to do with the geometry menu, then do everything we need to do with the properties menu, etc. Okay? Now, the way that MASTAN works is you go into a menu and you execute a command, and then down here, you're going to enter all the data necessary to build the model. And then as we start going down the rabbit hole, we're going to be building a truss and analyzing it together. Okay? I'm not going to say much about the file menus or the view menus. I think those are pretty self-explanatory, but there are some pretty good things worth mentioning. So things like export photo, you can print a photo, which is great for a homework assignment or a project, nudge, nudge, wink, wink. And then you can also generate a text report of all the results, like the displacements, the forces, and so on and so forth. And that'll be really valuable for your project as well. View, I think we can figure that part out. Okay. One thing that is worth mentioning right off the bat, and this will make this is really important, is about units. Okay, most high-level software packages, like take Abacus. I mean, they design space shuttles with Abacus. I mean, it's one of the most premier finite element analysis packages on the planet. Abacus uses no units. There's no internal unit system built. The thing about matrix analysis is whenever you're writing a software package, you can do one of two things. You can build a program that will do the unit conversions for you, or you can entrust the analyst to incorporate or to use their own unit system. And most high-level packages do the opposite. So Mastan does not define a pre-built unit system. You have to be consistent with the inputs that you use. So I highly recommend that whenever you're modeling a structure that you use your forces in kips and that your lengths are in inches. And so, and this will make more sense on Monday, but when you're modeling the structure, like for example, it's not 20 feet long, it's 240 inches long, okay? Some ground rules before we begin, some terminology. I'm going to use the term joint and node interchangeably, and I'm going to use the term member and element interchangeably, okay? Just right off the bat. So this truss that we're going to do has 5 nodes, and it has, I believe, 7 elements, okay? Just keep that in mind. Again, convert everything to consistent units before beginning. One nice thing is that Mastan will do the math for you, so you can use 6 times 12. It'll actually do the calculation. You'll see that in the handout. Sign conventions. Okay, this is important. Sign conventions, we need to report everything in consistent sign conventions. So what Mastan does and what most finite element packages do is they make a base assumption and apply it everywhere. So for example, in the x direction, anything going to the right is considered positive. So a displacement to the right, a force to the right. So if you're applying a load and it needs to go to the left, you enter a negative value. Okay? Does that make sense? If you're applying a downward force, you enter it in negative. Okay? Make sense? Tensile forces are positive in trusses. Okay? All right. Let's see. We'll stay in CD. All right, sorry, we'll stay in 2D and CD. We'll stay in 2D. You could expand all this into 3D, but we'll stay in 2D. Okay, so we're going to define a step-by-step process. We're going to define the geometry. We're going to define the properties. That's like the section of materials. We're going to define the conditions of the model. We're going to perform the analysis, which for us is literally just clicking a button. And then we're going to post-process the results. Post-processing the results is going to be like looking at the displacements and so on and so forth. Again, just starting at the menus, working our way over. This is the truss we're going to analyze. Let's go ahead and get started, okay? So I've given you all a handout, and I'm going to do this with you, okay? I'm going to try and go through it with you. It won't take very long. As we go through the handout, as you're, if you've got any questions, we'll pause periodically. This will be a fairly quick model to run, okay? So I've got Mastan pulled up right here, okay? So the first thing that I'm going to do is I'm going to go to File, Save As. And I'm going to save this model here. I'll put it on the desktop. And whenever you're doing this, I hate to be bring up MATLAB again, but the names for these models reflect MATLAB variable names. So don't put spaces in your file name. Don't start the file name with numbers. Use letters, numbers, and underscores. So I'm going to name this as example or X31. Okay, just to have it saved. Okay. So, all right. So what we're going to do is we're going to create the nodes first. So let me show you how this is going to work. So we're going to go to Geometry. We're going to go to Define Node. And we're going to start entering in coordinates. Now again, we have to enter the coordinates in inches, okay? So like the first node is going to be at 0, 0, 0, okay? So 0, 0, 0. So we'll hit Apply. And that'll create the first node. If you do that, you should see a node 1 pop on the screen. Now the second node is going to be at, its coordinates, right? It's going to be at 12, 0. But instead of saying 12, 0, what I'm going to do is say 12 times 12. And the cool thing is Mastan understands that because, I mean, it's calculating. This is based in MATLAB. So we'll hit 12, 12, comma 0, hit OK, or hit apply, and there we go. And then the same thing here, we'll do 24, hit apply. Now we'll do 6 times 12, and I think the height is 8 times 12. And then we'll do 18. Then when you're done, hit cancel. It should look something like this. By the way, I'll go to the slides here to make a couple points. Whenever you're defining geometry in Mastan, whenever you're defining a model, and this works for your project or your homework or anything, structural analysis packages don't really care where the origin is. Because, like for example, if I have a beam here that's 100 inches long, it's going to do the analysis by taking the coordinates of this point minus the coordinates of this point. So you could do 0, 0 and 100, 0. You could do 25, 0 and 125, 0. You could do negative 150, 25 and negative 50, 25. As long as the lateral distance between those two is 100, that's fine. You just need a consistent origin. So for this problem, we're choosing the origin at the bottom left. So if you look at the analytical model, this is the analytical model that we're going to use. This is just the nodes and the elements. And I'm saying the origin's right here. So this is 0, 0, 12, 0, 24, 0. But again, note that I'm converting that into inches. So when I input the coordinates, it looks like this. All right, I'm going to create the elements, and then I'm going to check and see how everybody's doing. So geometry, now we're going to define the elements. Defining the elements is really easy. All you have to do is literally just, click from node 1 to node 2, hit apply. Node 2 to node 3, hit apply. So I'm going to do the lateral ones first, node 4 to node 5, hit apply, then we'll do the diagonals. And hit apply. And when you're done, hit close. Okay. I'm going to walk around for a bit. I just want to see how everybody's doing on this part. We'll see if you've got the truss part figured out. Should look something like this in the window. We've got a lot of folks working on it. They're figuring it out. Figuring it out. There we go. Getting it worked out. Good, good. I like it. And some of you are working ahead. I'm fine if you work ahead. I'm not worried about that. If you need to work ahead, if you want to work ahead, that's fine. But I'm just going to maintain a reasonable pace to make sure we're all good. Okay, everybody good so far? Okay. Now, in this problem, what we're going to do, what we're going to do is define the properties. So like I said, we went to the geometry menu and defined the nodes and the elements. Now we're going to go to the properties for the materials and sections. For the example that we do today, we're going to use the library of shapes that are inside Mastan, and then on Monday we're going to create our own, so that way we'll know how to do both. So properties, we're going to define the section first. So the section is the shape, like what it looks like. And so what we're going to do is we've got, for this truss, we have W12 by 22s and W12 by 16s. So we're going to create each of those. So I'm going to go to the database, and this is all the rolled shapes in the United States. So we'll go to a 12 by 22, hit apply, then a 12 by 16, hit apply. So basically, so just so you're aware, the way the process works, we're going to define the sections, and then attach them. And the analogy that I like to use is defining the sections is like buying the buckets of paint, and then attaching the sections is like actually painting the walls with them. So we're actually painting the structure with these attachments. So we're going to attach the W12 by 22 to the horizontal members, and the W12 by 16 to the diagonals. So we will make sure we're on section 1, Click that, that, and that. Hit apply. You'll notice that it looks differently when you hit apply because the dashed line will change. Make sure that you click clear and then click the diagonals. So you click clear and then click the diagonals. Change this to section 2 and hit apply. So now what we've done is we have attached the W12 by 22 to all the members, but it doesn't know what material that they're made out of. So now we're going to make it steel. We're going to create steel. So I'm going to go to properties, define material. We're going to define a material. We're going to call it steel. All we need to worry about is E, and E is going to be 29,000 because it's in kips and inches. Again, consistent units. We're going to, let me move that off the microphone. Kips and inches. So we're going to hit apply. And then since every member is going to be steel, we're just going to go to properties, attach materials, and instead of selecting each individual member, just select all. And cancel. And if you've done that right, what should happen is now the truss is all solid lines. Okay? I love that Mastan gives you a simple visual cue to ensure that you've modeled it correctly. Every member, if it has a solid line, means that it has both a material and section attached. Okay? Does that make sense? All right. Everybody okay with this? Okay. All right. Next thing we need to do is apply our conditions. So conditions is Mastan's way of saying boundary conditions or fixities and loads. So we're going to do the fixities first. So fixities are your boundary conditions. So we're going to go conditions, define fixities. And the way that it works is we'll just do it node by node. So node 1 is restrained in the X and Y. So we'll click X and Y, hit apply, clear. And then node 3 is just the Y. So make sure and uncheck that. So if you're applying that, it's easy to not uncheck. So I hit apply. And by the way, if you've defined one incorrectly, you can always just redefine it and hit apply. It's okay. But if you do this correctly, you should have 2 over here and 1 here. Now what we're going to do is define the forces. And so if you notice here in this table, I put everything here in this table for you so you know where it is. I tried to make this handout really, like I didn't want you to have to keep flipping back and forth. So let's see, defining forces. So we have on node 2 and node 4, we have a negative 50 kip load. Why does it say negative 50 kip on Y? Because it's going downward. Hit apply, clear, and then on node 5, this one up here, we make that 0, but we make this positive 35. Let's see, I hope it's showing up here on the screen that you can see we've got this green arrow and these 2 green arrows here. So how are we doing? We check in with everybody so far. Is anybody having any major issues? Your geometry is not looking accurate. So let me show you what you can do. Is it that these were wrong, the coordinates? So what we can do is geometry, move nodes, so like this, move information. So it's currently you didn't change it to the feet, did you? So make sure you convert everything to inches when you do it. So okay. All right. Everybody good so far? Everybody good over here? Over here? All right, so at this point, the model is solved, or sorry, not solved. It's built. And so watch this. All you have to do is go to Analysis. We're going to do a static analysis that's first order elastic. Just click. Now, it might be angry at you because you have to change the analysis from a planar frame to a planar truss, because we're doing a truss type problem. You'll understand what that means maybe a little bit later. And hit apply. And if it's done correctly, you should see this analysis complete. And what if I told you, when I say the analysis is done, I mean the analysis is done. We have every single support reaction computed. Every single joint displacement in every direction, done. Every force in every member, done. It's done it all. It's crazy. You hit this little button and it just solves the whole structure for you. So, but I'm sure that you're sort of looking at the window and going, I mean, yeah, Dr. Mike, but I don't see anything, okay? That's where the results window comes into play. So if you go into the results window, you can start to see some things, okay? I'm going to hold off on the diagrams first. I'll tell you what, let's look at the results first. So we're going to go, I'm doing this in a little bit of a different order than what's on the handout. Let's go to results node displacements. So if you go to results node displacement, like for example, click node 2, it will tell you that node 2 has a horizontal displacement of 0.056 inches to the right and 0.157 inches downward. See that? Done. Okay. How about this? What happens if I click node 3? Node 3 has a horizontal displacement of 0.084 to the right, but why is it 0 in the y? That's the support. It's going to be 0 that way. So if I click node 1, what's it going to look like?
0,
0,
0.
0, right? Now, this is not an efficient way of looking at the data. If you want to look at it more efficiently, go to File and Create Report. And what I'll do is I'll just check the displacements and hit Apply. And you can see what it does is now what it does is it gives you the displacements at every joint broken up into X and Y, or every node broken up into X and Y. So you could take this, copy and paste it into Excel, which we'll talk a little bit about that on Monday and some things you need to look out for, but it sort of does it all for you. Does that make sense? So I'll show you some details about that a bit later. So I'm going to cancel that. You can look at element forces. So for example, if I click element 3, what do I have here in element 3? What's the only thing it reports? P equals negative 38.75. What does that mean? It is experiencing 38.75 kips in compression, right? So if it's positive, it's tension. If it's negative, it's compression. Boom, it gave you every force in every member. Here's something else that you can see. Watch this. Let's do a deflected shape. So let's go to results, diagrams. Let's do a deflected shape. And one of the things that I'm going to do is I'm going to change the scale to 40 and hit apply. And when I do that, I get this. Okay. Now, what you're doing with that scale factor, because you got to understand, this truss is 24 feet long and the displacements are only, like 0.05 inches or whatever. So we're upping the displacements up by like a factor of 40, so we can actually see visually what's going on. And if you want to have some fun with it, you can click the little animate button, hit apply. Once it does its thing, boo! You can actually see the structure go through the displacement, right? So again, what it's doing is it's computing the displacement at every joint in every direction and just plotting it, X and Y. So it's actually pretty cool that it can do that. I'm going to close the animation aspect. I'll turn the animate off, hit apply. One of the things that you can do is, let's say you want to put this picture in a report. You can go to File, Print Photo, we'll say to PNG. Put it on the desktop as deflection. And then if you go to the desktop, there's your picture, you know. Pretty nice to put in a report. So you don't have to like break out snipping tool and whatnot. You can just use this. So. Does this make sense? So ultimately what you're going to have to do, the reason that I wasn't able to assign submittal to is because you're going to do this for the truss that you chose, right? And we'll go back to that here in a bit on Monday. But and that's why I kind of wanted to talk about this at the beginning of class. If you get one of those emails that your truss has to change, don't spend all your time doing a Mastan model of truss 1 if you can't use truss 1 because it violated one of the conditions. Okay? Does that make sense? All right. Let's take a step back. Anybody have any questions? Did anybody have any trouble building the model? All right. So far, so good? All right. Then here's what I'm going to do. I've got, I'm going to stop the lecture here at this point. On Monday, here's what we're going to do on Monday. So on Monday, we're going to do another model. We're going to do a beam model. The other thing that we're going to do is I'm going to show you some tips in Excel on, like, what if I wanted the forces in every member? How do I easily query that data? And I'm going to show you that. I don't want to information overload you, so I'm going to show you that on Monday. That's all I have, everybody. You all have a wonderful, wonderful weekend.